Happy Monday to you. Unfortunately, I am not here today, so you get this wonderful video again. Thank you to all of you that are paying attention and paying along. If there comes a point in time, we can pause the video, or I should say you can pause the video and you can rewind it a little bit and you can hear what I had just said to see if it can be made a little bit clearer for you. So obviously today lesson 1's homework was due, but since I'm not there to stamp it, I'll check those tomorrow in class. But you will have lesson 2's homework due today in class, or I shouldn't say in class, it will be due tomorrow. Hopefully you get some work time today in class to work on. Okay? So what I would like you to do now is just in your tables, I'd like you to look at these 5 numbers and tell me which one doesn't belong. I'll give you 2 minutes. You don't need to pause the video. I'll keep the timer on here. 2 minutes to figure out which one doesn't belong and why. That is 1 minute into the discussion. 1 minute to go. $15 seconds. 10 seconds. I'm going to go in 3, 2, 1. Here we go with the reasons why that one of these is not like the other one. 4 of them are nice numbers, meaning 2 is a nice number. -2 is a nice number. -1/2 is a nice number. It's a fraction, but still a nice number. We're okay with that. 2.2 repeating is a nice number. Those are all what we like to call rational numbers, meaning we can write them as a fraction. Just as an FYI, this is 2 2/9, or 20/9. There it is as a fraction. The one that I don't like is D. D I don't like because it is irrational, meaning I can't write it as a fraction. That's why we don't like it. Okay? In this world, you have probably seen different number sets. So up at the top of page, turn my book to it. I should have had my book turned right to it. well, that top page you're looking at top page 14, I would like you to draw this diagram for you. Okay? So real numbers are just any number that you can think of is a real number. Okay? Rational numbers are numbers that we can write as fractions. Some examples would be like 7/8. 3 is a fraction. You don't look at it like it's a fraction, but remember we can always write it over 1. Okay? 1.5 is rational because we can write it as 3/2. And those are all rational numbers. Then a subgroup of rational numbers are numbers that we call integers. Integers have no decimals. So this would be like -7, +18, 56, -1,263. Those are all integers. No decimals on those. Whole numbers are the positive integers and 0. Those are the whole numbers. Natural numbers are positive integers that's supposed to be an E. Without zero. And our irrational numbers are numbers that can't be written as a fraction. So for instance, the square root of 2, pi, e, all of those type of numbers. Square root of 7 can't be written as a fraction. Okay? We're going to need those because we're going to be talking about discrete functions and their domains today and going forward. If you need time to continue to write this down at the top of page 14 or in an open space on page 14, pause the video here and then restart it when you're ready. Okay? So, now we are at, the wordage is at the bottom of page 14, but the work is going to go at the top of page 15. The Library of Congress in Washington, D.C. is considered the largest library in the world. They often receive boxes of books to be added to their collection. Since books can be quite heavy, they aren't shipped in big boxes. On average, each box contains 8 books. If, on average, each box contains 8 books, how many books are received in the library in 6 boxes, 10 boxes, or n boxes? Use a table, a graph, and equation to model this situation. Okay? Well, let's start with a table. Boxes is going to be what comes in, so that's my input, is the number of boxes. And then the number of books is what we're looking for. Would be over there. So if we have one box, on average, it contains 8 books. If we have 2 boxes, we would have now 16 books. If we had 3 boxes, we would have 24 books, and so on and so forth. Let's put this on a graph. Draw in our axes. Then we need to label our axes. So the number of boxes is going to be my independent variable, and we can go by ones there. We're good with that. The number of books is going to be the vertical, and looks like we're getting pretty big pretty quickly. I would say we could go by 8s. I mean, let's make it easy on ourselves. Let's go 8, 16, 24, 32, 40, 48, 56, 64, 72, 80, 88, 96, 104, 112, 128. Okay. So then we can plot some points here. So at 1, we're at 8. At 2, we're at 16. 3, we're at 24. And that pattern is going to continue, so we can keep going in that pattern. We're always adding 8 books to our library. Now, we can come up with an equation. It's linear. It's arithmetic because we're always adding 8 books. So let's call it B of n, B for books, is equal to, my first term was 8, plus 8 times n minus 1. Two ways then that we can find how many books we got, or how many books we have in 6 boxes. One way is we could plug in 6 into our function. B of 6 is going to equal 8 plus 8 times 6 minus 1. 6 minus 1 is 5. 8 times 5 is 40. And 8 plus 40 is 48. The other way that we could do that is we could go over on our graph and we can go up 6 boxes until we find what we're looking for, until we meet our graph, and then go over to see how many boxes it is, and it is 48. 2 ways of doing that. Oops, no, I missed. Okay. 10 boxes was the other one. 10 boxes, we could go up our chart here, or up our graph. We're going up and up and up and up and up. We get to there. So 10 boxes would be 80 books. Now, the domain for this function, since this function is discrete, this is a discrete function, we're not going to draw it in because we don't get a box and then all of a sudden it only has we get half of a box. We either get a box or we don't get a box. So since this function is discrete, the domain of this function is going to be the natural numbers. Okay? Or all of the integers greater than 1. What I would like you to do now is I'm going to give you 15 minutes, or we're going to pause the video here for 15 minutes, or however much time you need. I would like you to do numbers 2, 3, 4, 5, and 6, and 7. So I want you to do numbers 2 through 7 now. Probably give you a little bit more than 15 minutes. Probably give you closer to 25 minutes to get those done at your tables. Okay? So you're doing numbers 2 through 7 right now. Go. Mrs. Lucky, please pause the video here, and you can start it back when you're done. Here is the answers to number 2, or what your graph should look like. Again, it is going to be a discrete graph. Okay? And so after 3 hours, you will have 39 ebooks. After 5 hours, you will have 65 ebooks. The equation is after n hours, so there we go with that one. Number 3 looks like, here's what number 3 looks like, but number 3 was also asking how many, so now this equation is in minutes, how many books can she shelve in 3 hours? Well, that's different than 3 minutes, because 3 hours is 3 times 60 minutes is 180 minutes. And so what you've got to do is you've got to plug in 180 into your equation to find how many books she shelved in 3 hours. So then that would be 3 plus 3 times 180 minus 1. 180 minus 1 is 179. Three times 179 is 537. So that means that she shelved 540 books in 3 hours. That one you can't just go, because the units aren't the same, graph to problem, you have to get the units the same. Likewise for 5 hours, and so on and so forth. Okay? Oops, I think I skipped numbers 4 and 5 down here at the bottom. Would it make sense for any of these situations to be a time when 32.5 books have been shipped? For me, this would not, because you can't have 0.5 of a book. You either have the book or you don't. That's why it's also discrete and not continuous. They all are discrete. Here now in number 6, you're cutting a piece of paper into threes. This is a geometric sequence because you're cutting each piece into 3 pieces, so you're always multiplying by 3. So here is your table, your equation, and your graph. Then the domain of this function would be, again, sorry about that. Thought I had the pen selected. The domain of this function would be the natural numbers. Actually, I lied. Excuse me, pardon me. Not the natural. This one's going to be the whole numbers because we do have 0 cuts. That's 1 piece of paper. So we can include 0 on this one. Would it make sense to look for the number of pieces at 5.2 cuts? Nope. And it would. You either cut it or you don't. Would it make sense to look for the number of cuts it takes to make 53.6 papers? Again, nope, because it's got to be a multiple of 3. And it's got to be a whole number there because we can't have, when we cut it, we don't cut it into a portion of the paper. So here is what number 7 then looks like. Okay? So it's a percentage problem, so that means that it's geometric. So we're decreasing the amount of medicine that is in the dog's system is decreasing by 20% every hour. So here is what the graph should look like. Now notice what's different about this particular graph. This is not a discrete graph, because it doesn't, the medicine is wearing off over time. It's not, 1 hour later, now we're down 20%. 1 hour later, now we're down 20% more, and so on and so forth. This one is wearing off slowly over time at an average rate of 20% decrease per hour, which changes the domain of our function. The domain of our function now is all numbers greater than or equal to 0. Okay? So because it's greater than or equal to 0 now, we can have decimal points. Does it make sense to look for the amount of active medicine at 3.8 hours? Yes, it does, because 3.8 hours is an actual time frame that you might have in so you give the dog the medicine, 3.8 hours later, you might have to figure out where, if you can give them another pill, or if you can do something along that. Would it make sense to know when there's 35 milligrams of medicine left? Yes, it would, because that's going to tell us when almost half the meds have worn off. Okay? So in this particular case, this is a continuous graph, a continuous situation, and so therefore we have differences in our domains and what we can look for and what we can get. 6 was discrete. 7 was continuous. And we explained that when we were talking about those. What needs to be considered when looking at a situation in context, deciding if it's best fit with a discrete or continuous model? I mean, I'm going to flat out say that logic is going to determine a lot of that. Okay? Can you have something that works over time? On Friday, we talked in my classes about can you produce half of a bottle? Or can you produce a whole bottle, or can you produce part of a bottle? If you can have parts of something, then it's a continuous type 1. Okay? Love it. Okay? So with that being said, you now can start working on the Ready, Set, Goes for this lesson. They are due tomorrow. Thanks for playing along. Again, I will stamp 2 homeworks tomorrow when I return.